So now, continuing with limits, the computation and calculation of certain limits usually boils down to either some trigonometric limit, which is what we just saw in the previous video, or some algebraic manipulation involving, developing a certain expression or expressing it as a factor and then simplifying terms or multiplying by the conjugate over an expression involving roots, which we also did in the last video. Another type of technique that you learn and that you'll be asked about is that it involves the so-called squeeze theorem. And okay, so I'll just give you an example. So supposedly we want to find out what is the limit when x approaches 1, say x minus 1 to the cube times, say, sine of 1 over x minus 1. This is equal to what? And with this example, I actually want to cover all the possible things that you may encounter in the exam. It's always going to be the same thing. So basically here you cannot just evaluate and apply the rule for the product of two things, because while the limit of x minus 1 cube exists and it's equal to 0 because x goes to 1, sine of 1 over x minus 1 on the other hand oscillates infinitely often near 1, and so this is the kind of graph that you already saw in the past. It's a very wild behavior near 1 on either side, but it doesn't converge to anything. So you cannot just say the limit is 0 times the limit of something, because the limit of sine over 1 of the sine of 1 over x minus 1 does not exist. This doesn't apply. So here, whenever you have something like this, you apply the squeeze theorem. And so what happens is you have two functions, x minus 1 cube, which goes to 0 as x approaches 1, and the other function is sine of 1 over x minus 1, which is bounded. This is a crucial thing. So one of them is something that goes to 0, and the other one is one that is bounded. This could also be so examples of functions that will be bounded: cosine of something, sine of something. They will always be bounded between minus 1 and 1. So you have the product of two functions, one which goes to 0, and the other one which is bounded. Okay, so once you recognize that, you can always say that, well, the sine of 1 over x minus 1 in absolute value is always less than or equal to 1 and less than or equal to 0. So this means that if you say you multiply also by the absolute value of x minus 1 cubed, you will be able to say then that 0 will be less than x minus 1 cubed sine of 1 over x minus 1 is less than or equal to x minus 1 cube in absolute value. what this means is that that minus the absolute value of x minus 1 cube, I mean you can bring the cube outside of the absolute value, is less than or equal to x minus 1 cubed sine of 1 over x minus 1, which is in turn less than or equal to the absolute value of x minus 1 cube. Okay, and this function here goes to 0, and this function here goes to 0 as well. So what's in between must go to 0. So this is by the squeeze theorem, by the squeeze theorem. And if you have questions about how we derive this inequality, I mean this inequality down here from the one up here, so let's look at a drawing. If I say that say x in absolute value is less than or equal to 3, that means that x is somewhere in between minus 3 and 3. If it were, say, minus 4, then the absolute value of minus 4 would be equal to 4, which is greater than or equal to 3. It is greater than 3. So the possible values of x must be between minus 3 and 3. Everything else will have an absolute value greater than 3. And so whatever is here on the right hand side, when you bound the absolute value, gives you a bound like this. So minus that expression here on the right will bound x from below, and this same expression will bound x from above. So this is what we have here. The absolute value of this expression is bounded by this positive expression. So minus that expression will bound what's inside the absolute value from below, and will bound this from above. And so the conclusion here is always the same. And by the squeeze theorem, you know that what's in between goes to 0. And so we can go over a couple more examples. Let's try to say we want to compute the limit as x approaches 0 of cosine of 1 over x to the 7th power. Does this limit exist? Well, it does. Remember that all the questions it will ask you, they have to do with the squeeze theorem. Well, you need to apply the squeeze theorem. Will boil down to the same thing. So you have a product of two functions, x, which goes to 0 as, well, x itself goes to 0, and you have a function that is bounded. Right? Cosine of 1 over x to the 7th is always bounded, because cosine of anything is bounded. So in fact, I could have, so don't be confused when in the exam, when you see the exam and you see maybe a different power here, like 100, or some other complicated expression like cosine of 1 over sine of x. It doesn't matter what we put inside the cosine. Cosine is always bounded. So you put some expression inside. Cosine may look complicated. It doesn't matter. Cosine is bounded. Cosine of whatever you put inside the cosine is going to be bounded by 1 in absolute value. It doesn't matter whether I put a power of x, or as I said, 1 over sine or 1 over sine cube of x, cosine of something is always bounded between minus 1 and 1. So the absolute value is bounded by 1, and so this implies, again, the same thing. We have, this is the function that is bounded. It means that x times the cosine of 1 over x over 7 is bounded from above by the absolute value of x. As we say now, we copy this thing inside the absolute value, and we say that this is going to be less than or equal to what we have on the right, so x, and minus, and it's going to be bounded below by minus this expression on the right. And this goes to 0, and this goes to 0 as well, as x goes to 0. And so by the squeeze theorem, then this goes to 0 as well. So it is the same thing. And one final example. Again, just to make sure, x goes to 0, and we have x squared times cosine of 1 over sine of x. This limit is equal to what? Okay, so what we say again, when if there are two, this is a product of two functions. One that goes to 0, which is x squared. This goes to 0 as x approaches 0. And cosine of 1 over sine x. Again, I told you not to be confused about what's inside the cosine. Before I even look at what's inside, I know this is going to be bounded in absolute value by 1, no matter what I put in here. This is always going to be bounded by 1, so if I put 1 over sine of x, it's not going to make any difference. It's going to be bounded between, the cosine of that is going to be bounded between minus 1 and 1, regardless. So you have two functions, one that goes to 0 times some other function that is bounded. So we use this inequality actually to multiply everything on both sides and get the x squared is then less than or equal to x squared. Right? X squared is always positive, so that's why I'm not writing the absolute value of x squared. But then again, once we just obtain this inequality, the second inequality here, by multiplying by x squared, this one up here. So on the right hand side we get x squared, and on the left hand side we get x squared times cosine of 1 over sine x. And then, just like before, then this expression inside the absolute value will be bounded from above by the expression on the right, and by minus the expression on the right from below. Again, we can say safely, we already know that minus x squared goes to 0, and x squared as well. And finally, by squeeze theorem, this quantity here goes to 0. Okay, so it's the same thing. No matter what you do, so that there are other variants. I mean, you can, that's what happens if instead of x squared here we use, say, sine of x squared. Sine of x goes to 0 as x approaches 0. So that wouldn't change anything. So we would just need to write sine of x here instead of x. But there's always the same structure. You always have the same structure, and whenever we ask you to use the squeeze theorem, or you think you have to apply the squeeze theorem, it always follows the same thing. Same principle. You identify a function that goes to 0, which in this case would be sine of x squared, and function that is bounded. And the trick here is to realize that you don't really need to pay attention to what's inside the cosine, the argument of cosine, because no matter what you put inside, cosine of that is going to be bounded between -1 and 1. No matter how complicated the expression is inside the cosine, that's going to be bounded by 1 in absolute value. So okay, so to finish, remember that when you have limits like this, so something goes to 0 times a bounded function, you probably need to apply the squeeze theorem if that bounded function is not really approaching any limit, and always break it into two, as a product of two functions, one again going to 0, the other one bounded. It's very easy to recognize when you have something like a power of x times cosine or sine. Either cosine or sine will satisfy the same requirements. They're both bounded by 1 in absolute value. And if you multiply by a power of x, that goes to 0 as x approaches 0. So the exact same proof will apply to all of these situations. Identify a function that goes to 0, in this case this expression here, and then a function that is bounded, that. And you're multiplying both of them, and so you start from the bound for the bounded function, which is this inequality here, and you multiply by the absolute value of the function that you know already approaches 0. Once you do that, then the procedure is the same, and you arrive at the conclusion in the same way as we've done in these examples.